Good afternoon, students.
ఇద్దరు అల్లమ్మ కూడా వచ్చిందా?
Okay, students. Yesterday we have seen some topics of real analysis. So today we'll see the unit 1. So in unit 1, I have told what are the important topics we have here. So first unit is real number system and completeness. Okay. So in this first we have the concept of, if you'll see in page number 3. Okay, in page number 3, we have that real numbers as an ordered field. So for that one, we have the concept that is in set R of real numbers. There are two binary operations, plus and dot, called addition and multiplication, satisfying the following properties. Okay, these properties are important. So if you know about this concept, you have even in the 4th semester, you have that is a group and semi-group and subgroup and also abelian group. There you will have the concept of this one: commutative property, associative property, identity property, and inverse property. Okay, with respect of addition and also with respect of multiplication. If any binary operations, that is with respect of addition means plus, and with respect of multiplication means we'll use dot or circle or even cross symbol. That is, we can use this one or this one or like this. So these three represent for the multiplication. Okay, so if any set of real numbers, if they satisfy these additive properties and also multiplicative properties, then the set of numbers are called as, they form as ordered field. Okay, so in addition, so the properties are, first one we have with respect of addition, we have first one is commutative property. Okay, commutative property, or else we can call it as commutative law. In 10th class you have studied it is a commutative law, or else we call it as commutative axiom also. Okay, so here if a comma b are any two numbers which are present in the real numbers, okay, they belongs to real numbers, means that is capital R, then we'll write commutative property is a plus b is equals to b plus a for all a comma b belongs to R. Okay, so whenever the two elements a and b, they belongs to set of real numbers, then if they satisfy this property, then the two numbers are satisfying the property of commutative property, that is a plus b is equals to b plus a. And second one is associative property. Okay, associative property means we'll take three elements, that is a, b, c. So that will be a plus b plus c is equals to a plus b plus c for all a comma b comma c belongs to R. Okay, so this is the associative property. Next, third one is identity, additive identity property, that is identity. That is a plus 0 is equals to 0 plus a is equals to a for all a belongs to R. So this is the we call it as identity property, or else additive identity also we call. Okay, so next, so fourth one is inverse property. Okay, so in or else it is called as additive inverse also. Okay, inverse property is, so we have for each sentence is there, you can check in textbook. For each a in R, there exists minus a in R such that A plus minus A is equals to minus A plus A is equals to 0. Okay. Here whatever minus A is there, that is called as inverse. So inverse of A is minus A. So when you add number and its inverse, we will get the additive identity here, that it is equals to 0. So this is the for all A belongs to R. Okay. This is the inverse property. Similarly, for multiplication also, you will have multiplicative properties. So these all addition properties, they are represented as A1, A2, A3, and this is A4. Okay. Next, for the multiplicative properties, we will represent them as M1. So M1, same, it is commutative property. So in this addition is there, no? Here we will have the multiplication. That is A dot B is equals to B dot A for all A comma B belongs to R. Okay. So next one is M2. M2 is the associative property. That is A into B into C is equals to A into B into C. Okay. This is the associative property. Just I am writing M1 and M2. Here you can see what are those properties. So A into B into C for all A comma B comma C belongs to R. Okay. Next M3 is, here we have identity property. No, here we call it as a same identity property, or else it is called as multiplicative identity. So multiplicative identity means you can write there exists 1 belongs to R such that A into 1 is equals to 1 into A is equals to A. Okay. So here identity property, identity element is 0. Here for the multiplication identity element is 1. Okay. For all A belongs to R. And next we have M4. So M4 is same. Here we have identity property. No, next one is the inverse, and we call it as multiplicative inverse. So multiplicative inverse means there exists for each A not equals to 0 in R. That means A value is not equals to 0. There exists A inverse belongs to R. Here inverse is minus A. In multiplication, what we have to do when we do A plus identity element 0, we are getting the element itself. Whenever we do the inverse, that is element, its inverse, when we do, we have to get the identity element here. So what is the identity element here? Identity element is 1. So here for the inverse, you have to get the answer as 1. So how you will get 1? A into A inverse is equals to 1. Such that A into A inverse or A inverse into A is equals to 1. Okay. This is the inverse property. And for the multiplication, you will have one more property. That is a distributive property will be there. That is called as M5. So if any set, it satisfies the, with respect to of addition, these 4 properties, and with respect to of multiplication, these 5 properties, then it forms an ordered field. Okay. So here M5 is, so M5 is distributive property. Distributive property. Okay. So one is extra for the multiplication. That is A into B plus C is equals to A into B plus A into C. So this is the distributive law for all A comma B comma C belongs to R. Okay. So this is called as a distributive property. In this, we have multiplication is there and also addition is there. Okay. Combination of the two operations we have. So whenever a set satisfies these all properties, then it is called as a, that whatever the set is called is as a ordered field. Okay. So next we have concept of modulus or absolute value of any element. So if any element is given in the set, for that how to find the absolute value or modulus of that value. This one you have studied even in first SEM also. Modulus or absolute value. So absolute value of element A. So here let A belongs to this. A belongs to R means R represent here real numbers. The absolute value of A, we denote it as denoted by mod A is defined by that is modulus of A is equals to A. If A is greater than or equals to 0, it is equals to minus A. If A is less than equals to 0. Okay. This condition you should know while solving the theorems or else in the problems also. So in unit 4 we have problems are there, no? There whenever we'll take the modulus of this one or absolute value of any element, it should be, if it is a positive element, if it is greater than or equals to 0, it is a negative element if it is less than 0. Okay. So next after this we have what is a countable set and also definition of countable set. So definition of countable set, before that you should know the concept what is a set. First if you know what is a set and what is a subset, so whatever the theorems are there in the real analysis, those all will have the concept of set and subset. So in lower classes, that is in 10th standard, you have studied about the set. So set it is a collection of well-defined objects. Well-defined means if you write any set, if you think S is any set, whatever the elements you are writing in this set, they should have some definition or they should have some meaning. Okay. Then only such type of elements, when they are writing in flower brackets, we call that S as a set. Okay. So the definition of set is, it is a collection of well-defined objects. You can write it as set of even numbers. Okay. Set of even numbers means, what are even numbers? 2, 4, 6, 8, 10, like this, so on. Okay. So they have some meaning. Means whatever these elements are there, either you can tell they have the difference of 2 or else they are the set of even numbers. So such type, and we know that even the set, whatever we are writing, we can write it in roster form and also set builder form. Okay. So what is set? If you know, it's enough for you. And set builder form means, in some questions they will ask the question in the form of set builder form also. This is the roster form. And this is roster form. Okay. Set builder form means, okay, we can write this one only as S is equals to X equals to 2n, such that this symbol we have, no, we call it as a such that we can write like this, or else we can write like this also. Okay. The meaning of that one is same. So in some problems you will see as these two dots, or else as a slash also you will be seeing there. Okay. So it is X equals to 2n such that X belongs to R, where n is equals to 1, 2, 3, so on. Okay. So whenever you write whatever these values are there in this form, this is called as set builder form. If you are writing directly the numbers, then we call it as a roster form. How this is formed, you are writing that form, this one. How these numbers are formed? Whenever you are taking x value as 12, where n values are from 1, 2, 3, you are getting these values. Okay. So the whatever the description of the set is there, when you write in this form, we call it as a set builder form. Okay. And subset means if you take any set, A is equals to 1, 2, 3, 4, 5, 6, 7, 8. Okay. I'm taking only finite set. So if you are taking the set A as these elements and B, you are choosing the elements from the set only. So alternately, if you choose, what you will get 2, 4, 6, 8. Means whatever these elements are there, these are present in this one. Okay. These, then we call the set B as a subset of A. Okay. So if you get the same, if you write the same element, means even B also 1, 2, 3, 4, 5, 6, 7, 8. Okay, means whatever the elements we are present in set A, same elements you are having in set B. Then we can call it as set A is subset or equals to set B. Okay. Why we are only subset means we use symbol like this. If it is only subset means if only some elements are there, then we'll write only the symbol as this one. If the elements are also same, then we put the symbol as equals to. Okay. So subset means whatever the elements you have, if A and B are two sets such that every element of A is an element of B, then we say that A is subset of B and denoted by this symbol. Okay. So in theorems and also even in problems, we use the concept of set and subset. Okay. So next we have the concept of countable set. So before the countable set, in the definition of countable set, we have concept of function. So in lower classes, already you have studied what is a function and a different type of functions are there. That is one-to-one function, many-to-one function, one-to-many function, many-to-many functions. 4 different types of functions will be there. And also we have onto function is there. So function is nothing but whatever it will be mapping between any two sets. F is a function which is mapping between set A and set B. So usually you will represent like this, no? F is mapping from A to B. Okay. So F is any function, it is mapping from A to B. That is set A to set B. So whenever we will write like this, set A is equals to 1, 2, 3, 4. Okay. Set B is equals to A, B, C, D. Okay. And this is the function. Okay. Mapping from A to B. So we call it as a domain. And this is codomain. Okay. So domain and codomain here. So when we call f as a function means each and every element of domain, if it has some image in B, set B means compulsory whatever the elements are present in A, it should have the images in set B. Then means if you have one more element here, it is not having the image here means it is not called as a function. Whenever the elements present in its domain, it should have the image in codomain. Then we call that function as a, is whatever the mapping is here done, that is a function. Okay. And you can see that it should have compulsory only one image. Okay. So that means 3, it is to one function. One-to-one function means what? Each and every element in set A should have only one image in set B. Okay. Means this element should not be repeated. So it should have one-to-many means only one element to any two numbers here or any single element to 3 images. Okay. But just we need here the concept of what is domain and what is codomain. Next we have one more is range will be there. Range means if each and every element of this, it is having the pre-image, then range, how many numbers they are having the images, that number is called as a range. Means here range is set B. That means range is equals to, in some cases, range is equals to codomain. Okay. So that is we can write A comma B comma C comma D. Suppose you think one more element is there, E. Then range is not equals to codomain. Why? Because in codomain E is also there, but E is not having any image here. So in this case, range is not equals to codomain. Range is only A, B, C, D. Okay. This is not having image, no. So this element you will not consider as a range. Okay. Oh, if a function is satisfying only one condition, that is one-to-one function. Or else like this also will be there in textbook. One-to-one function. We call it as a surrogate injection. Okay. This is called as injection. And if your function is satisfying only onto function, if a set is satisfying only onto function, then we call it as a surjection. Okay. If both one and onto, then we call it as a bijection. This is a very important one. In many problems and in theorems, you will see this word bijection. Bijection means whenever the set it is one-to-one function and also it is onto function, then we call it as a bijection. Okay. So next, through this concept of one and onto, we have the countable set definition. And one more concept is there, that is a similar set. When two sets are called as they are similar to each other, that condition is similar set. Okay, let A and B are non-empty sets. A is similar to B if there exists a one-to-one and on-to map from A to B. Okay, so this definition you may not have in your textbook. You can take this one. Let A and B are non-empty sets. A is similar to B. You are able to see now, okay? A similar to B if there exists a one-to-one and on-to map from A to B. Okay. So means A is one set, B is another set. If it is satisfying both one-to-one relation and also on-to relation, then those two sets are called as similar sets. Okay. And we represent it as, that is A, like this. Will, if you see this symbol, it is called as similar. Okay. That means A is similar to B. So next, if we have the definition of finite set. Finite set means a non-empty set is said to be finite if it is similar to Sn for some n belongs to n. So countable set, to know the concept of countable set, we need the definition of similar sets. We need the definition is what is one-to-one function, what is on-to function, and another one is finite set. Okay. So finite set A non-empty set. A non-empty set is said to be finite set if it is similar to SN. Okay. For some n belongs to capital N. Here SN form, if a non-empty set is in the form of SN form, then we call it as a finite set where this n is means n are whatever the n we are taking the numbers, those are the natural numbers. Okay. So you can write finite set as like this. Sn is initial segment of n. So that is n values here we are substituting here. So that is 1, 2, 3, 4, so on up till n. That means in place of n, we are taking 1, 2, 3, 4. So whatever the initial segment of n means, whatever the numbers are there in the natural numbers, those numbers we are writing this one. This is the finite set. So it is ending here, no? End point is there. If you write so on, means then it is called as an infinite set. Okay. So infinite set means which is not finite set, we can tell, or else it is not similar to Sn. So whatever the Sn is there, if it is not similar to that one, then we call that set as infinite set. Now the main thing is countable set. Countable. So countable set definition is a set A is said to be countable. Three conditions are there to say that one set is countable set. A set A is said to be countable set if first condition is A is empty set. So A is empty set means what? No elements are there in that set. So you can count, no? So no elements means 0. So the countability of that set is here is 0 we can write. Next one is, second one is A is finite set. So here finite set means, so if you have the limited elements in that set, so you can count that as 1, 2, 3, 4. If 5 elements are there, means you can write the element, the countability of the set is 5 here. So the countability of set, that we call it as a cardinality. Okay. Third one is A is similar to N. A is similar to N. Means that is, like this set A is similar to N means what? Means it should be one-to-one function and also it should be on-to function. Then we can tell that whatever the given set is there, two sets are countable sets. That's why I have told yesterday one theorem is there, no? Set of rational numbers is countable. So there we use this third one, third condition. That is A is similar to N means we have to establish there one-to-one and on-to relation. That is equivalence relation. If you establish there, then we can say that rational numbers are countable to, that means rational numbers are countable. Okay. You have theorem. There we'll use the same, these three concepts, and we'll find the proof for that one. So one condition is this one, and also another one is even if it is a countably infinite also, we can tell that we can find the countability of that set. Okay. So this is only just the concept of countability. You can see the theorems are there in test 2. It is page number 9. You have the definition of the countable set. Okay. Next, page number 10. you have the main theorem. It is the set of all rational numbers is countable. So here it has been drawn in the table, and they have established a one-to-one correspondence between the set of rational numbers and natural numbers. So here instead of A, it is a real rational numbers with respect of natural numbers. In the table they have written the numbers, and in page number 11, if you see, that is a rational natural numbers they have written in the first part, and in the rational numbers whatever they are mapping with that one they have written in the second column. Okay, so just you practice this one proof. It is important. You may get for 5 marks or else for 10 marks question. Next one, 11th page number, if you see, it is the set of real numbers is not countable. Okay, yesterday I have told that whatever the real numbers are there, those are means they are the combination of rational numbers, irrational numbers, and also natural numbers, whole numbers, and integers. Okay, in between of any two rational numbers, infinite number of irrational numbers will be there, and also rational numbers will be there. So that's why we will be unable to count those numbers. That's why the real numbers are not countable. So that proof is given with the help of the some examples are given. You can see the proof of this theorem also. 12th page number and 11th page number. These two theorems are important. And one more, sometimes you may get for 5 marks question, 12th page number only. Root 2 is not rational number. Okay. So we have to prove that root 2 is not rational number. We know that rational number means it will be in the form of P by Q, where P and Q are integers such that Q is not equals to 0. Okay. So with the help of that proof only, definition of the rational number, you have to show that root 2 is not a rational number. Okay. So these are the three important theorems in first part. And next we have the concept of bounded and unbounded sets. So if you know the concept of here, what is upper bound, what is lower bound, and what is infimum, what is supremum, then easily you can do the theorems proof. Okay. So before going to what is upper bound and lower bound, first thing is we have in the definitions, you can see it is mentioned that aggregate is there. So the definition of aggregate is a non-empty subset of real numbers. Okay. We know that real numbers means, so from positive infinity to that is negative infinity to positive infinity, whatever the numbers present in between of those, we call them as a real numbers. So if we'll take from those real numbers some numbers, we have already studied what is subset, no? If we'll take some elements from that subset, then that elements are called as an aggregate of a real number. So in definitions, you can see the word aggregate is there. Means aggregate in the sense it is a non-empty subset of real numbers. Okay. In page number 13, you have the definition of what is aggregate. It is a non-empty subset of real numbers. Okay, we call it as a aggregate, or simply aggregate of a real number, or simply we call it as a aggregate. Next we have the concept of what is upper bound and what is lower bound of a set. Any set will be given. In that set we have to find what is upper bound and what is lower bound. Okay, upper bound So upper bound definition is let S be any subset of R. Any subset of R, then a real number then a real number, capital M. Okay, capital M is called an upper bound of S if every element of S is less than or equal to M. Okay, that is X is less than or equals to M for all X belongs to S. Okay, this is the definition of upper bound. Let S be any subset of R. Means you can R else directly you can write aggregate also. Let S be aggregate of R, then a real number M is called an upper bound of S. Okay, S is any set we are taking. You can take the example like this. S is equals to 2, 3, 5, 10. Okay. So S is any set, we have 2, 3, 5, 10. These are the elements of the real numbers. No, some numbers we have taken from that. So that's why S is called as a subset of real numbers. So if you take any number from this set, M is called an upper. So from this, if you take any number which is the highest value, okay, this is the highest value in upper bound means this is the highest value. M we are taking. M is called an upper bound of S. So this is the highest value. M 10 is called as upper bound of S if every element of S. If other elements are what? 2, 3, 5. So every element of S is less than or equal to M. So if you will take this 10, if you consider this as a capital M, whatever the other elements are there, those are less than. Okay, equal to. Why we are taking equal to symbol means equal to this one. So this, the number itself and also the other elements. So this number is called as upper bound when other elements of the set are less than or equals to 10. Okay. So what is the, whatever the, if it is a finite set, highest value will be there. No, that value is called as upper bound of the set. Okay. So here it is only the, it is whatever the number 10 is there, it is not only the one element which is the upper bound. After 10, you may have 11, 12, 13, 14, like this on. So the set it considers only the 10 as a one element. So we are taking this number as a upper bound. A set may have many infinite. We can call it as infinite number of upper bounds will be there. So outside the set, whatever the outside the sets are, but here whatever the number it is there, the other elements are less than 1. So we are considering it is in the set. So we are considering this number as the upper bound. Okay. So whichever the definition is, see here, a real number M means which is the highest value, or you are taking that as a capital M, is called as upper bound of S if every element of S means each and every, you may have many, more numbers also. Okay. Each and every element of S is less than or equals to M. These are all less than or equals to M. So this is the definition of upper bound. If we take for this one only lower bound. So lower bound means same. Let S be any subset of a, then a real number. So don't get confusion. You can take instead of small capital M, small m you can take. Okay. Then a real number small m is called as lower bound. Okay. Lower bound of S if every element of S is greater than. Okay. Greater than or equal to smaller. That is X is greater than or equals to here smaller. So here, this is the element no least. whatever the lowest element is there, that lowest element, what did we call? Then a real number here, this is the smaller, is called as lower bound of S if each and every element of S is greater than this element, no? Okay. So greater than or equals to even this element also. So such type of whatever the element you are taking from the set S, it is called as a lower bound. Okay. For this also, here whatever outside the set, you may have infinite number of lower bounds also. Okay. So here you may have infinite number of upper bounds, even you may have infinite number of lower bounds also. But here in the set we are considering this as the least value, so it is called as lower bound. It is considered as the greatest value, so it is called as upper bound. Okay. So if it is a upper bound means we call it as a bounded above. Okay. So if it is upper bound means we call it as bounded above. That set is bounded above. And if it is lower bound means we call it as a bounded below. Okay. So here, if a set is both bounded above and bounded below, means yes, if a set contains upper bound and also if a set contains lower bound, then we call that set is a bounded set. Okay. The definition of bounded set is a set if it is bounded above and also bounded below, then we call it as a bounded set. If it is not bounded above and not bounded below, or else one is bounded, another one is not bounded, means we call it as an unbounded set. So you have the definition in your textbook, you can see there. And if you think, if you see natural numbers, so 1, 2, 3, 4, 5 like this, up to infinity we have. Here we know the least value, means that means lower bound is existing here, but we don't know the highest value here. So in such case, what will happen? Least bound means lower bound is existing, that is bounded below it is there, but we don't know what is the upper bound here. So that's why we call it as an unbounded set, or the set of natural numbers is not bounded. Okay. You can take the example of natural numbers here. Next, in this only one more important concept is infimum and supremum. Okay. So we have studied upper bound and lower bound. No? Next, the concept is greatest lower bound and also least upper bound. So if you know these concepts while solving the theorems and also problems, it will be easy for you. Least upper bound or else we call it as a supremum. Okay. Supremum means least upper bound. So in all the upper bounds, whatever the least element is there, that least element is called as a supremum. Okay. You can write in shortcut the smallest of all upper bounds. We consider it as a least upper bound and it is called as a supremum. You can take example here. That is, if you take in the number line, if we have 0 here and it is -1, here +1 is there. Okay. So this is the upper bound. No, highest value is this one. After 1 also you may have one here. Is after 1 you may have 2, you may have 3, you may have 4 or 5 like this. But first thing is we are considering only that is in between of 0, -1 and 1. In that elements, 1 is the highest value. These are also highest values. From these all highest values, which is the least upper bound? 1 is the least upper bound, no? So that's why we consider this as the supremum. In before example also, S is equals to, we have written out 2, 3, 5, 10. After 10, you may have infinite number of upper bounds. But after this, these are all greater numbers. No? This is only the least number. So here the supremum of this set S is here 10. Okay. Means for all, it will be there like this. We can't tell. For some directly finite set is there, means there you can find which is the supremum and which is the infimum. But if you have them in the form of the set builder form, we have seen just now. So if the question is given in that form, that you have to find which is the upper bound and which is the lower bound there. So you can take here the example. That is 1 by n will be there, no? S is equals to, so if the question is like this, S is equals to 1 by n such that n belongs to n. So if it is given like this, means you have to write the set. So that is n is here natural numbers, no? So substitute here 1, 2, 3, 4 like that, okay? So 1 by 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, so on up to infinity we have, okay? So 1 by 1 means the value is, you can take here 1. After that 1 by 2 means 0 0.5 and 1 by 3 means 0 0.3 like that. After that 0 0.25, so on you will get, okay? Here whatever the elements are there, it is starting from 1, okay? And if you go on like this, last number you think it is a infinity. So when you write in this form, what will happen? 1 by infinity value is 0. Means whatever the values are there in this set, they are tending to 0. Okay? They are tending to 0. Means here whatever the elements are present in set, they are from 1, it is the starting, and they are tending to 0 here. So the highest value is what here? 1 is the highest value. Okay? So here it is the supremum of this set 1. Supremum is equals to here 1. Why? Because each and every element of X is less than or equals to 1. Each and every element of the set is less than or equals to 1. And whatever the elements are there, those elements are less than or equals to 1. So this element is called as a supremum. That is, it is the upper bound and it is the least. After this, you may have the numbers 1.5, 2, 2.5, other numbers will be there. From those all upper bounds, this is the least one. So that's why we call it as a supremum of this one. But 0, this is the infimum. So why? Because this, whatever the set is there, it is tending to 0. So sometimes upper bound or lower bound, they may exist or they may or may not exist in set. Here 0 is not there in the set, no. But we are getting the value as that is 1 by infinity, means these values are tending to 0. So here whatever the lower bound is there, it is not exist in the set. But we are getting the lower bound. In some cases, we may get the lower bound or even upper bound. It may or may not exist in the set. Okay. So if you take that is greatest lower bound, it is called as infimum. Greatest lower bound in your textbook, you can see shortcut like this will be there. G dash L dash B. And it is called as infimum. Okay. So it is called as greatest of all lower bounds. Okay. Greatest of all lower bounds. In this also say whatever the least element is there. Here -1 is there. No, this is the least element we have. So from that all the, this is the, here we may have -2, -3, -4 like this. No, greatest of them is this one. -1 is the greatest value. No? So greatest of all the lower bounds, this is the one we have. So we call it as a GLB and it is called as infimum. Okay. So these are the concepts you should know. And bounded set definition is there. You can see from the textbook. Some example problems are there. And in this, one theorem is there. Completeness maximum and deductance maximum is there. This is you may get for 10 marks question. That is a page number 16 you have. 1.5.17 it is there, no? 1.5.17 and also 1.5.21. It is a combination of those two. And proof you have in page number 17. Okay. So this is one important one. So these are the important questions in first unit. I have told starting two theorems. See MEQ questions you can see in page number 21. So these are first define a countable set. Just now I have told the definition. No? The definition, and you have to show that the set of rational numbers is countable. And one more is show that every non-empty subset of n has infimum. So this theorem you have in page number 8. I missed this one. Okay. Page number 8, 1.3.3, well ordering principle is there. No? Just now we have seen the infimum definition. No? From that you have to show this one. Means every non-empty subset of n. For natural numbers, whatever the subset you are taking, that subset will have compulsory least element. So why? Because natural numbers, they are starting from 1, 2, 3, 4. No. So whatever the starting element is there, compulsory, the starting element will be the lower bound. So it will be having the infimum. So that only proof he has asked that one. This question is also asked for 5 marks or else sometimes 10 marks also it is asked. Next, third question. Just now I have told, no, 17 page number. State the completeness maximum and the deductance version of the maximum. Establish the equivalence of these two. Okay. And the short answers, if you'll see, define LUB and GLB. That is lower, least upper bound and greatest lower bound of an aggregate, and give example. So this is about the unit 1. Unit 2, yesterday I have told, no, what is a interval and also open interval, closed interval, endpoints will be there, no? That concept will be there. For endpoints, like this. Before going to the endpoints, even we have the definition of what is neighborhood of a point. Neighborhood of a neighborhood of a point means let us be a subset of R and alpha belongs to R. Alpha is any element which belongs to capital R. Then we say that S is, I'm writing it short like this, NBD, neighborhood of alpha, if there exists delta greater than 0. Delta is any arbitrary constant. Okay, small delta greater than 0 such that alpha minus delta comma alpha plus delta is contained in S. This is called as symbol subset, no? Contained. So then we call that set S is having the neighborhood of that point. If you see the representation here, whatever the element is there, that from the set S you are taking one element, that is alpha. Okay. So surrounding any element, if you are taking surrounding of that one, place whatever it will be there on right hand side and also on the left hand side. Whatever the elements are present, that we are called as a neighborhood of that point. Okay. So here alpha, it will be alpha minus delta, and it will be alpha plus delta. Okay. So if alpha is any element which belongs to real numbers such that on its neighborhood, if you have alpha minus delta and alpha plus delta, these two elements. So if you think 1 is there, any point you are taking on the number line. So 1 plus delta, sorry, minus 1 minus delta and also 1 plus delta. So here 1 means before that up till here what will have 0.9, no? And before that means here 1.1, 1.2, 1.3, so on values will be there. So these 0.9, 0.8, whatever the values are there, these values and also these values should be present in the set yes. If you are taking the set yes as equals to 1, 1.1, 1.2 and also 0.9, whatever the values will be there, no? If the set is containing these neighborhood values in that set, then we call the point 1. The point 1 is neighborhood of the set. Okay. So after this neighborhood of a point, we have intervals are there, 4 intervals. Try to see the definition from the textbook. This is the open interval. Okay. And we know these are endpoints or boundary points. And here, this whatever the first point is there, this is called infimum and this is called supremum of a interval. Remember, infimum of a open interval is A, supremum of open interval is B. Even for the whatever the closed interval is there, they also will have the same. This is the closed interval. This will represent as A less than X less than B. This is A less than or equals to X less than or equals to B. Semi-open, semi-closed, those also you can take from the textbook. Okay. So in this, we have the concept of what is a limit point is there and also what is open set, what is closed set. And in this theorems are, just you see the important theorems here. So already time is completed. 25 page number 2.2.13, 2.2.14. These two are the essay questions. That is 10 marks questions are there. So next class we'll see just the introduction of what is the limit point of a set and also what is open set and what is closed set. Next we'll go to the third unit and next block 2 and block 3 we try to complete up to the completion of the classes. Okay, we'll see on 25th we have class. Okay.
Okay, ma'am. Thank you, ma'am.